Hello everyone. Today we are going to learn what is digital signature, what is the how actual the digital signature works, and the most important topic, that is Elgamal digital signature, in which we can see the algorithm also and some examples so that you can understand better.
So this is a generic model of digital signature. A digital signature is an authentication mechanism that enables the creator of a message to attach a code. Okay, we are attaching some code that act as a signature. Typically, the signature is formed by taking the hash of the message and then encrypting the message with the creator's private key. The signature guarantees the source and the integrity of the message. You can see here, first this message which Bob wants to send or to transmit to the Alice. First, this message converted into the hash. Okay, you already see the hash value. Suppose we are using SHA-512. Okay, and then that particular hash will be encrypted with the help of Bob's private key to form the signature. Okay, so what is the input? The input to the algorithms are message, which is in the form of hash value, okay, and the Bob private key to produce this particular signature. Okay, now what will be transmitted to the Alice or to the other end? Okay, so any other user, say Alice, okay, can verify the signature using verification algorithm whose inputs are the message, this original message, okay, plus the signature and Bob's public key. So in this algorithm, the original message was fed and the signature, which will be created with the help of hash of the message, and which will be encrypted with the help of Bob's private key. Okay, so that particular thing will be decrypted by the Bob's public key, obviously, and once again we get the hash value actually, and the hash value of this particular message will be compared. So this particular algorithm returns that particular signature which comes from the Bob is valid or not. So this is a simple generic model of a digital signature. Now what we learn here, that message is in the form of hash, and then that hash will be encrypted with the help of Bob's private key. So same thing will be happening in Elgamal digital signature, only that is one method which we can say we can that particular algorithm will be fed in this place so that we can get the signature. Okay, now let's understand what is Elgamal digital signature and in what way that particular algorithm will work. So as we already see in digital signature, the private key of the sender will be used for encrypting the message, or we can say the hash value. Okay, so in Elgamal also it involves the use of private key for encryption and public key for decryption. Here there are two global elements, which are they? That is one prime number q and alpha, which is primitive root of q. So before going to the example of Elgamal digital signature, you must know what is primitive root of q. That I will show you in the next slide. Okay. So there are two global elements, that is q and alpha. Now user A, or we can say the sender, generates a public and a private key pair as follows. Okay, in Elgamal digital signature, it will create a private key and public key pair. How they will create it? Let's see. One thing we already know, we already seen that Diffie-Hellman algorithm also, that x means it's a private key, y means it's a public key. Okay, so it's a private key of A means Alice, it's a public key of A means Alice. What is q? Q is our prime number. And what is alpha? Alpha is a primitive root of q. If you already know what is primitive root, then it's okay. Otherwise, I will explain in next slide. Okay. Okay. So first, generate a random integer xa, but it have some condition that xa is greater than 1 and it is less than q minus 1. Suppose our prime number is 19, then xa must be greater than 1 and less than 18. Is that clear? Not 18 also. Next, compute a public key, that is ya. It will be computed by ya is equal to alpha raised to xa mod q. Okay, so xa we already generated here, and that will be simply put it here, and mod q will be fine, and we will generate a public key of a. Now a's private key is xa and a's public key is, there are three things in the public key in Elgamal digital signature. Okay, first one is q, it is globally known, alpha, and ya, which we will compute here.
Okay, now we see how the sender will sign the message. Okay, this is just an algorithm, we can say. Okay, the exact example, with the help of example, we will see after this completion of algorithm. Okay, for signing a message by the sender side, मैंने आपको पहले ही कहा था, the message first converted into hash value, and then that hash value will be encrypted with the help of sender's private key. Okay, तो यहाँ पे आप देख सकते हो, the first to sign a message, user A first compute the hash. Suppose our message is whatever our message is, suppose hello, how are you? So first we have to create the hash, say m, such that m is an integer in the range of, it must be greater than 0 and less than q minus 1. What is our q? Q is a prime number. Okay, most of the time message will be given in the examination and q is also given in the examination, so that you can compute whole things properly, because we also know we are not able to convert the hash value of the message directly. Okay, so what A will do then for digitally sign? First, choose a random integer k, that is key, such that k is greater than 1 and less than q minus 1, that is prime number minus 1. But k will be not be selected randomly. The GCD of this particular k and q minus 1 is equal to 1. For example, q is the prime number is 19, so q minus 1 is 18. So the GCD of 18, and suppose I am taking k equal to 3, is equal, it must be 1. So if I take k equal to 3 and 18, GCD is not 1. GCD is greater common divisor is 3. Okay, suppose I am taking k is equal to 5 and q minus 1 is 18, so k equal to 5 is correct, because GCD of 5 and 18 is 1. Okay, so that is k is relatively prime to q minus 1. Now relatively prime is somewhat easy compared to primitive root. So before starting with starting the example, we will understand what the primitive root is, and then we will proceed with the numericals. Okay, now second step is compute S1, that is signature 1. In Elgamal digital signature, the signature consists of S1 and S2. You can see here the signature consists of S1 and S2. Now how this S1 and S2 will be computed? So S1 is equal to alpha raised to k mod q. Whatever the answer will be there, that is our S1. Next thing is we have to compute k inverse. Now why we are computing k inverse? Because we have to use in signature 2, that is S2. Okay, so k inverse, how to find k inverse? K inverse is equal to k inverse mod q minus 1. Okay, so that is compute the inverse of k modulo q minus 1, we will get k inverse. When we get the k inverse, we are able to compute signature 2, that is S2. What is S2? S2 is equal to k inverse the message that will be generated from here, which is in integer and less than q minus 1, minus xa, which is a private integer which will be selected by sender, that we are already seen in the previous slide. So m minus xa into s1. S1 will be generated from here. Mod q minus 1 will gives s2. So in Elgamal digital signature, the signature consists of the pair S1 and S2. Now we see how to verify this signature by the receiver side. So any receiver can verify the signature by following ways. First, he or she will compute verification 1 and then verification 2. If both the answer are equal, then he or she can assure that the signature is valid. Okay. For computing V1, alpha raised to m mod q will be computed, and for V2, YA, that is public key of Alice, sender. Okay. YA raised to S1 into S1 raised to S2 mod q. The signature is valid if the value of V1 and V2 will same. Let's see this whole process with the help of example. So before going to the example of Elgamal digital signature, first we must know that what is primitive root. In examination, the value of q and alpha is already given. If the value of alpha is not given, then you have to find, because alpha is a primitive root of q such that you have to select that particular alpha. Okay. So how we can say the alpha is a primitive root of q, or any number is a primitive root of a prime? So let's q be a prime number, then alpha is a primitive root of q if the power of alpha mod q generates all integer from 1 to q minus 1 in some permutation. For example, we know that we are selecting q is equal to suppose 7. Our prime number is 7. Then alpha mod 7, suppose we are selecting alpha is equal to 2. 2 mod 7, then 2 raised to 2 mod 7, then 2 raised to 3 mod 7 up to 2 raised to 6 mod 7 must generates all integers from 1 to 6. Why 1 to 6? Because our prime number is 7. If our prime number is 19, then all integer must be from 1 to 18. Let's see with the help of example. Suppose the prime number q is 7, then primitive root is 3. If you take alpha equal to 2, then 2 is not a primitive root of 7. Okay, 3 is a primitive root of 7 because the power of 3 mod 7 generates all integer from 1 to 6. Why till 6? Because the prime number is 7. If our prime number is 19, then all the integers must be from 1 to 18, and which all are distinct. सेम नंबर नहीं चलेगा. द सारे जो भी नंबर्स हमें आंसर्स मिलेंगे एक तो डिस्टिंक्ट होने चाहिए, अलग ही होने चाहिए, सारे नंबर्स सेम नहीं होने चाहिए, और q minus 1 तक ही आंसर्स होना चाहिए. फॉर एग्जांपल यू कैन सी हियर 3 raised to 1 mod 7, 3 raised to 2 mod 7 up to 3 raised to 6 we have to check, that is q minus 1. ओके, जो भी आंसर हमें मिलेगा वो 1 to q minus 1 के अंदर ही होने चाहिए. डेट इज अवर प्राइम नंबर इज 7, सो इट मस्ट बी फ्रॉम 1 to 6 and all are distinct. आप देख सकते हो कहीं पे भी ये आंसर्स रिपीट नहीं हो रहे. सो आई कैन से 3 is a primitive root of 7. Let's even another example. Why I'm taking this example of primitive root? Because in Elgamal digital signature we are taking alpha is equal to 10 and q is equal to 19, which is our prime number. Okay, so I can say 10 is a primitive root of 19 because 10 raised to 1 mod 19 up to 10 raised to q minus 1, that is 18 mod 19, all the answers are distinct and it is from 1 to 18. You can see here. Okay, let's see the example. Here we are taking a prime number q, that is 19, and alpha is equal to 10, which is primitive root of 19. Now user A generates a public key private key pair as follows. First, Alice will select one random integer, that is a private key, which is greater than 1 and less than q minus 1. Q minus 1 is 18 and the 16 is greater than 1. So condition fulfills. Then Alice will compute the public key with the help of YA is equal to alpha raised to XA mod q. What is our alpha? Alpha is 10. What is our x is 16? Mode 19. What is the answer? The answer is 4. So the private key of Alice is 16 and the public key of Alice is 4. But in Elgamal digital signature, the public key is in the pair of three things, that is YA, alpha and Q. So the public key of Alice is 19, 10 and 4. This will be globally known as a public key of Alice. Okay. Suppose Alice want to sign a message with the hash value that is m equal to 14. मैंने आपको पहले ही कहा था जो भी हमारा हैश होगा मैसेज का that must be in the form of integer, okay, and it must be greater than 0 and less than q minus 1. So here suppose the hash of the particular message is 14 and Alice want to sign this 14. Okay, now Alice will sign the message with the help of Alice private key that we already know. Okay, now Alice chooses a key which is 5. Why it is 5? Because it is relatively prime to 18. If you find the GCD of 5 and 18, that must be 1. That is 1. If we select k equal to 3, that is not valid because the GCD of 3 and 18 is not 1, it is 3. So 3 is not relatively prime to 18. That's why we select k equal to 5. Now for signature 1, what is the formula? Alpha raised to k mod q. What is our alpha? 10. What is the key? 5 mod 19. What is the answer? Signature 1 is 3. Now for signature 2, we must first compute k inverse. So k inverse is somewhat difficult. So how to calculate k inverse? Suppose the value of k is 5. So 5 inverse mod 18 we have to find. 5 inverse mod 18. So in this way we can find if 5 inverse if you want to find 5 inverse mod 18, you must have to find 5 into one number mod 18 must be 1. If I starts from 1, 5 into 1 is 5. 5 mod 18 is equal to 5, not 1. Okay. If I take 2, 5 2s are 10. 10 mod 18 is 10. If I take 3, 15 mod 18 is 15. If I take 4, 5 4s are 20 mod 18 is equal to 2. Okay. Suppose if I take 10, so 50 mod 18 does not equal to 1. You can check, you have to check with all possible numbers from starting from 1. If I take 11, so 11 into 5 is 55. 55 mod 18 is equal to 1. So by multiplying which number we get mod 18 equal to 1? By multiplying 11. So what is the answer of 5 inverse mod 18? The answer is 11. Okay. So the value of k inverse is 11. So with the help of k inverse we can find signature 2, that is S2. What is S, the formula? K inverse message minus XA into S1 mod Q minus N. What is our k inverse? K inverse is 11. What is M? M you can see here, M is equal to 14. Then what is our XA? XA is equal to 16. What is our S1? We already generated here, that is 3. So the evaluation of this portion is minus 374 mod 18. The answer is 4, but you may have problem that how to find the negative integer mod 18 or negative integer mod any value. For finding this we have a simple formula. Suppose we have a negative value, suppose minus a mod b is same as b minus a mod b. Is it clear? Negative number minus number is equal to, that is a b minus a mod b. So what is our b? B is 18. You can see this is our a, this is b. B is 18. Now minus, what is our a? 374 mod, and what is our b? 18. If you calculate 374 mod 18, you get the answer 14. So 18 minus 14 is 4. So this is how you can get the negative integer mode any number values. Is it clear? Okay. Now the signature 1 and signature 2 will be added with the message and send it to the receiver. Okay. Now how receiver will be verified? With the help of V1 and V2. Okay, let's calculate what is the value of V1 and what is the value of V2, so that we can say the signature is valid or not. So Bob can verify the signature as follows. It will first compute V1, that is equal to alpha raised to m mod q. What is our alpha? 10. What is m? 14. Mod 90. The answer is 16. And for calculating V2, what is the formula? Public key of L is, that is YA raised to S1 and S1 raised to S2 mod Q. So sometimes if you not select the value properly, the answer of this particular expression will be very large number, and very large number mode any number will be, for finding that particular number is difficult. Okay, so select the value appropriately. So what is our YA? 4. What is our signature 1? 3. 4 raised to 3 into 3 raised to 4 mod 19. What is the value of 4 raised to 3 and 3 raised to 4? 5184. Okay, 5184. Now 5184 mod 19 is 16. Here you can check the value of V1 is equivalent to value of V2. So Bob can say the signature is valid and the message comes from Alice only. Okay, thus the signature is valid. So this is how the Elgamal digital signature work. Let's take another example. Only one minor changes I will done. Let's see. So here is a minor change, that is alpha is equal to 3. Okay, that is also a primitive root of 19. You can calculate accordingly that we discussed previously. Okay, and check the answer is valid or not. So if you have any query regarding this video or regarding the Elgamal digital signature, you can contact me. Thank you.